Good afternoon, everyone, and welcome to today's IEEE-USA webinar, AI Grid Analytics Applications. I'm your host, Jonathan Cho. Our guests for today are Jim Lynch and David Schlane from Electrical Grid Monitoring Incorporated. Jim is a seasoned business development professional with a proven track record of success. With over 25 years of experience in sales and advanced software solutions, big data applications, machine learning, and process optimization, he has consistently driven results across diverse industries. Over the past decade, he has focused on delivering innovative solutions to electrical utilities, helping them transition their analytic applications to the cloud and enabling them to supply safe and reliable power at the lowest possible cost. David has 35 years of experience in the energy sector, including 20 years in oil and gas and 15 years in the utility industry. His expertise includes reliability, maintenance, advanced controls, and optimization. He obtained his RCM2 certification in 2003 and has helped organizations transition to proactive and eventually predictive reliability programs. Without further ado, I'll now pass it off to our guests. Welcome, David and Jim. We're very excited to hear what you have in store for our audience today.
Excellent. Thank you, Jonathan.
Thanks.
And
Thanks, Jonathan. Hi, David.
thank you, everyone, for your time today and for the opportunity to talk to you about predictive modeling using overhead distribution data. As Jonathan mentioned in his introduction, Jim and I have been involved in reliability and optimization as applied to many sectors in the energy industry our entire careers. So we've dedicated our lives to it. So welcome, and today we will be covering the following topics. Technological advancement over the past few years, how decisions are made to help organizations with operational efficiency, how data can and should be utilized, the AI and machine learning hype that we all hear on a daily basis, reliability maintenance fundamentals as applied to an industry where it is very difficult to see electricity flow, how to apply these principles to vegetation and row management and power delivery, where the data comes from, power line disturbances and how they can be used in decision making, building predictive models with the data you have, and how to apply those processes to improve applications like vegetation management programs. And then we can open the line up for Q&A. So let's get started. It is always interesting to talk about technological advancements in the past 50 years. I threw up this example to display that, but let's look at an example that we've seen in the last half century. So the item on the left is the actual computer that took man to the moon on July 6, 1969. Pretty unimpressive. It's about 24 by 13 by 7. It weighed 70 pounds, had 2 kilobytes of memory, a 2 megahertz processor, 2-digit numeric only keypad for input, and the display was, as you can see on the right there, a very thin alphanumeric only in black and white. Conversely, on the right is a modern smartphone. I think everybody, probably down to the age of the teens, has one of these, and you see it in their hands all the time, right? These are machines that are about 5 ounces or a quarter of a pound. They have about 2 gigabytes of memory on average, 3 gigahertz processors as a minimum, full QWERTY keyboards, and the display is high resolution full color. So in 50 years, we've moved from a clunky device that took us to the moon to something that's 270 times more powerful in that 50-year period. So I'll leave it up to you to determine if your phone can land us on the moon. To me, it's amazing to imagine how far we have come with the technology in the last 54 years. Today, computing power, the mechanism for delivering artificial intelligence, is not even in the conversation anymore. It is a given. We have dismissed computers as that source. So now let's talk a little bit about more about the data and how we use data. So if you have data, you have knowledge, right? It stands to make sense that if you have more data, then you have better knowledge. Well, there's a couple of gentlemen that said not so fast. So these are very famous data scientists. I'll start with the first one that's a little more familiar to everyone. That's Albert Einstein, who discovered the theory of relativity, better exemplified by the famous equation of energy, or E equals mc squared. Einstein used data by collecting it and analyzing it to develop and refine his theories. He famously said that information is not knowledge. That highlights the importance of interpreting and understanding data to extract meaningful insights. The other gentleman in the lower photo is an astronomer, very famous scientist named Clifford Stoll. Uh, I don't know if anybody's heard of Clifford, but he helped American authorities capture Russian KGB computer hacker Marcus Hess in 1986. Now, if you can imagine the tools available in 1986 and how difficult it would have been to capture an overseas hacker trying to hack USC Berkeley to gain intellectual property as part of a Russian spy conspiracy. So Clifford famously said, and this is a long one, but see if you can follow the pattern here. Data is not information. Information is not knowledge. Knowledge is not understanding, and understanding is not wisdom. So Clifford was highlighting the importance of going beyond raw data and again to drive meaningful insights. So by that logic alone, then data cannot alone be knowledge. You can't just make that leap of faith. So can data become knowledge? Yes, absolutely. Data alone is simply structured transactions. Information results from processing that data, and knowledge is actually how you use the data. So it's only valuable if it aids you in decision making. So the conclusion is that knowledge can be obtained from data. So now let's look at a couple of very misconstrued, misinterpreted, and misused terms that are floating around every day. You can't watch a news cycle without hearing one of these terms. And a lot of misconceptions that come from AI, right? A lot of people commingle AI with androids. Well, I guess you could call an android a part of an AI system, but it's not the only AI system. So artificial intelligence is about getting computers to mimic human capabilities. Examples of this are integrated into our daily lives. If you have a later model vehicle, it is safe to assume that it has features like lane departure, warnings, even steering assist to automatically help keep you on the road. This is a great example of artificial intelligence. The vehicle is using cameras and sensors to detect lane markings to provide steering assistance to the driver to keep him on the road. That is an exact definition of artificial intelligence. Now, machine learning is a subset of AI, where you train machines to follow logic patterns. So these logic patterns are derived from data that guides the desired behaviors. So if we go back to the car example, autonomous vehicles use cameras to calculate clearance around the vehicle, and they modify the speed, may brake, in order to maintain some clearance. And that's used for changing lanes, for coming to stoplights. So this is the learned behavior the car is being trained to perform. The data collected is used to improve the machine learning algorithms, improving its performance over time. So it gets smarter with more data and performs better.
You know, what's really interesting here is AI's been around a long time, a long time. Think of walking up to a grocery store door and it automatically opening. That's the simplest form of AI. Normally a host at Walmart would open the door for you and ask you if you want a buggy. So AI's always been around. It's just been getting smarter. And machine learning, I think it's important because we'll talk about patterns in a while here. But you learn from patterns. I'm certain all of us driving down the road would see an 8-sided red sign and know that that pattern means stop. It doesn't need to say stop on it, or you just know you're coming to an intersection, you see an 8-sided red sign. Highly likely you recognize the pattern. So it's important that, you know, the machine learning learns the patterns and it feeds the AI to make it smarter. Now they have, my friend tells me they have AI in the doors when they see moose approaching grocery store doors in Alaska. They don't open up for the moose, but they do recognize people, and that's all about the pattern. So this stuff's been around a while, and it's interesting as we talk more about it, and we'll be applying it here.
Excellent. Thanks, Jim, for those examples. Associating these two terms, they play a pivotal role today in power delivery reliability, right? Patterns to define causes of wildfires are being analyzed every day by utility data scientists, and mechanisms are to reduce the root causes are being implemented. So we see that more and more in the utility space. It's just a little more difficult to apply to electricity flow where you can't see what's actually happening. Well, if we look at the hype around AI and machine learning, um, there's a lot of, like I said, misconstrued theories and ideas about what AI is. People are afraid of it because of this. There's a lot of movies produced around AI and what what can happen if it gets out of control. But in essence, AI is useful today, right? We can use those patterns to learn from and actually make our process and daily activities much more efficient. And they're driving real business value. So what we're looking at here is the market cap by the largest corporation down to about the 10th on that list. So you can't go even a day without hearing about it, as I said before, but it comes in many forms, right? So AI systems everywhere today for content creation, applications, IoT data, and they come in many flavors. I'm sure a lot of you in the audience have heard of Chat GPT or OpenAI. There's Claude AI, there's Grok AI, and many others that are coming online. Those are all content providers and kind of part of the search engine world. But if you look at the figure on the right of your screen, today's leaders in market cap are almost all high-tech companies leading the AI and machine learning fields. So if you were to look at this back in 2001, it would be flipped, and the AI leaders of today, which are the tech companies, would be on the bottom of the list, and they replace the oil barons. So any kind of an energy company, anybody related to fossil fuels and oil and gas. So AI and machine learning are here to stay, and many consider them as the fifth industrial revolution. So interesting term I heard the other day. All right, if we look at some actual reliability maintenance fundamentals, for those of you who are familiar with reliability, there's many tools available for us to, to help us analyze things like root causes, fishbone charts, for instance. There's other tools like FMEAs, or failure mode effects analysis. Those are like heat maps, allowing you to define all of the failure modes around a failure and actually see the data contributing to that, so that the heat map will tell you where the areas of concern are. And lastly, we have a P to F curve, which is a prediction of failure based on, it can be based on time, but it's not really. Today, we might use sensors and other sensory equipment to help us determine when an item or an asset is about to fail. So if we apply this to the utility, you look at time-based maintenance, which had its useful purpose about 50 years ago, but today it's been proven as unreliable and costly and simply just does not work, right? I'll give you an example of that. Um, if you look at scheduling your oil change in your vehicle, let's say over the pandemic, most of us didn't drive our vehicles very much, right? And so if we follow the manufacturer's label on when we should change the oil, that would be every 3,500 miles or every 6 months. So if we did change the oil every 6 months, there's all sorts of errors or problems that you can induce. So this is a great example of time-based maintenance and why it doesn't work, because some of the items that could occur would be in removing the filter, the oil filter, or inserting a new oil filter, you could cross thread, right? Which then causes an oil leak. You could use the wrong oil. So these are areas where you may not have had to do the maintenance, but you did, and because of that, you induced other error. So time-based programs just don't work anymore. And a great example of this in the utility field is veg management and row management. Right, row is right of way, usually applied to transmission. But these are sciences now. So in the current day, a lot of utilities use schedule plans for their trimming. So they use a 3 to 5 year schedule. They'll schedule that. The work orders are automated. The crews go out based on those schedules. And what happens is you send a crew out to a location, and based on the variance, because as we all know, weather patterns change. You could have a monsoon season, you could have a drought season. So vegetation will grow at varying rates. So you can't depend on that to understand that a schedule will apply to that maintenance practice. So the more efficient way to do it is by employing proactive maintenance, right? Uh, s- these practices can save utilities tens of millions of operational maintenance expenses, also referred to as O&M costs. And O&M is bad for a utility. So they're graded on the amount of O&M expense they have. So it's a negative. The next revolutionary change that is coming to power delivery is really predictive technology. Um, Similar to with rotating equipment such as motors or turbines, you can apply several sensors to help determine when that motor is going to fail. So as I said before, vibration analysis and heat analysis are two very important sensing technologies that are applied to rotating equipment. As you see the vibration increase or increment, that indicates that a motor is probably more likely to fail. And by experience in applying AI and machine learning principles, you can get a good idea of when that rotating equipment is going to fail. So now, applying this to the power delivery industry, counting power line anomalies is a good way to establish if vegetation is encroaching on power lines, very similar to vibration analysis. When a tree rubs up against a line or lays on a line, you get a certain vibration on that power line. There's certain technologies, overhead line sensors that can actually detect that, measure it, and send that information to operators. Also, when trees rub or lay on lines, they cause arcing or momentary faults that are cleared usually with protective devices like fuses or reclosers. If we can measure the frequency of these momentary faults and correlate data like wind and satellite imagery, we can get a clearer understanding of a potential issue that could cause an eventual power outage. So identifying and locating these events can help utilities prevent failures. and again, move their vegetation management program from time-based to proactive. So utilities face unique reliability factors in that it is very difficult to determine the life of power delivery assets, right? How do you determine how long a fuse is going to last? A lot of the experienced line crews out there can actually, you know, figure these things out from experience, but through attrition, there's a lot of loss of that native knowledge. So we have to depend more and more on technology to help us. Part of these unique failures, for instance, how do you determine the life of an overhead conductor, right? The manufacturer may tell you that that conductor has a 15 to 40-year life, but with all the variability out there, you can't actually determine what that life is. It may be short-lived because you have external factors, maybe extreme heat, maybe extreme cold, ice, high humidity, salt, fog. So all of these factors can significantly decrease the life of that conductor. It's important to understand these principles because, for instance, root cause analysis, where the fishbone charts are used with sensor data to help identify the root cause of equipment failure, can significantly improve your programs. The FMEA, or failure mode effects analysis, can help utility list all failure modes, and the online data helps determine when you're approaching critical mass for the asset failure. And finally, sensors used today are helping utilities determine when equipment is approaching failure before it happens. So now we're getting into the predictive part of maintenance. And that's usually observed very similar to the rotating equipment through P to F curves, which can now be developed for items like vegetation encroachment, right? I'll give you an example. If you start seeing that these disturbances are increasing in frequency and they're correlated with wind, then we can get a good idea that it's trees rubbing on a line, right? And if you have a electrical signature of a waveform that actually tells you what that, the really replicates the characteristics of a tree encroachment, then you're starting to get a fuller picture. And so that P to F curve and the predictability is becoming a reality. So now let's look at some typical practices in the industry. Today, we've seen everything from reactive to time-based to proactive and predictive, depending on the utility. So some utilities are a little more sophisticated. Maybe they had to. There was different drivers to why they're a little more sophisticated than others, but it doesn't necessarily correlate with the size of the utility or the number of customers or meters they have. So there are predominantly three maintenance practices used by utilities. So, and if we speak specifically to vegetation management, the first is reactive. This is where utility line crews are dispatched to power down situations. So they may not have any clue as to why the power's down. They'll roll a crew out there. The crew will start driving the line. They'll find an issue where a tree has fallen on a line, knocked it down. And so now they're troubleshooting, they're fixing the problem, and that is very reactive, right? And it's very costly. So for obvious reasons, you'd like to be a little more efficient on the maintenance methodology applied. Another method is time-based maintenance, right? As discussed previously, most utilities in the US and North America as a whole use a schedule that is planned out 3 to 5 years in advance for both distribution and transmission vegetation management programs. So in transmission, the trimming and use of herbicides and fertilizers and many other methods to control vegetation is called row management, right of way. And there's an entire science around it, right? There's utilizing beneficial vegetation and having that grow so that it drowns out the bad vegetation that grows tall and can become an issue. is there's an entire science behind that. So there's a lot of assets that they have in herbicide management to be able to manage that whole process. In distribution, it's a little simpler because it's a matter of going out and trimming, right? However, there's a lot of rural areas where um, somebody may have a piece of land and a single phase line, and the utilities can't see that, so they proactively can't go onto the land. So there's issues with rights and accessing. So really, they depend on customers to actually call those in. So that's all part of time based, and that can become reactive as well. So since vegetation doesn't grow at the same rate every year, schedule based vegetation programs just don't work. They're costly and inefficient. During drought seasons, the vegetation won't grow very much, and during monsoon seasons, you might have explosion of vegetation. So the one thing you can count on is that there's variabilities in the process. The most preferred method is obviously proactive and predictive technologies, and we'll look at how those are applied in just a bit. But these methodologies can help utilities determine when trees need to be trimmed as opposed to on a schedule. For example, overhead line sensing technology. As I indicated before, if we can detect those momentaries that are coming across and our sensors are actually measuring, and we correlate that with wind data and actually satellite imagery, you can actually see so I'll run through a scenario. You get a sign or a notification from a system that says, hey, you have an increased number of momentaries coming from this area, which correlate with wind speed. Okay, so every time that timestamp of the wind occurs, a gust occurs, we also get the waveform that's distorted, and we get a notification saying, hey, you have an issue. So if those correlate, it's most likely either the lines or phases are slapping together, or you have a tree encroachment. So that's how you can actually move to the proactive, and then we'll look in a little bit how to get more predictive on it. So vegetation management issues are huge for utilities, right? I think the average, which I looked at, this is 2-year-old data, so it may have increased by then, but the average across all utilities in the US was around $20 million a year spent on vegetation management programs. That's a lot of money. Some utilities with very difficult regions, very difficult topologies, might have higher forested areas, spend actually in the surpassing 100 million annually in maintenance costs directly attributed to vegetation management. In addition to the financial burden, vegetation also poses significant safety risks, not only to line crews but the public as well. Once a line gets on the ground, it's extremely dangerous, and a lot of people may not see it if it's not arcing. So it's a huge safety issue. So they can also cause wildfires, right? So having about, I think the average was about 20% of wildfires in California back in 2018 were attributed to utility lines. So that is also a big issue, right? And what was happening is you had this beetle that was eating the trees, killing the trees, and those trees would then become an ignition source. So if a line was close to it, arced in any way, or had corona, it could light that tree on fire and start the process. So vegetation growth is highly, as I said, inconsistent, but you also don't know when these trees are dying, right? So that can be a major issue. So insects, lightning, soil quality, decaying root systems, all of which can reduce a tree's lifespan. When this occurs, trees end up becoming that fuel for wildfires. So very important to understand, the regulation around trimming, whether it's 10 feet, 15 feet, every state, every utility commission is going to have a different set of regulations. But the good thing is these solutions that detect these, as I described, can be capitalized. So while you're saving utilities millions of dollars in annual maintenance expense, they're also capitalizing the equipment that helps. So it's almost like a double benefit for the utility, because capital expenses are not a measurement for utility when they're getting a rate increase. So that's music to the ears of many utility CEOs. So now let's talk about a little bit about where the data comes from. All right. So in the right-hand corner, I'm showing a typical overhead line sensor solution. The platform that line sensor solution sends its data to, and then maybe the imagery that we talked about coming from satellites or imagery actually helping you. All of these three elements help you determine whether you have tree encroachment or not. So basically, back to the whole conversation around AI and machine learning, we're taking that raw data, those electrical impulse signals that are created from trees, rubbing on lines or laying on lines or breaking lines, and actually turning that data into real information that the utility uses. And then that information becomes knowledge. So with that knowledge, they get smarter, and now you can see the whole picture of AI coming together. So this information is collected by analytics platforms, and then they provide applications to notify utilities of those issues. So the line sensors are essentially a combination of intelligent communicating computers hanging on a line and oscilloscopes. So they provide waveforms, and power engineers can actually use those waveforms to detect momentary fault and anomalies that are occurring because of not only just vegetation encroachment, but also from effects of equipment or looming of equipment failure, animals running on the line, or birds landing on the line. They all create noise, or what I call useful noise, in the system that our sensors can actually detect. So the next step in that process would be to actually locate it, right? So once you determine that you have an anomaly, you define the anomaly, you detect it, you categorize it. Now what you want to do is you want to actually locate it and inform the utility of where that fault is coming from. So knowing all of that, now you can start seeing a picture of how you can significantly reduce the O&M costs in a utility by making them smarter, getting them the data they need to turn that into knowledge. In addition, sensors have onboard accelerometers. So, without having local wind or weather service data, you can actually use the sensors themselves to determine if every time there's a timestamp for a anomaly, that the sensor is actually moving as well at that time. So you're not only getting one form of data, but you're getting it in several forms, which more data means better knowledge. These sensors are strategically located on your feeders and laterals to let utility operations know if there are any issues with their medium to high voltage lines. Sensors are installed directly on a distribution or transmission conductor, and they're measuring several parameters. They're measuring conductor temperature, current, voltage, humidity, and all of the physical measurements that I mentioned earlier, like vibration and actual movement of that sensor. So all of that data combined then starts giving you a better idea of what's actually happening on the line. That's why one of our taglines, as you'll see, is we say eyes on the grid. So when you correlate all of this data that you're getting, all this raw data with the wind and satellite imagery, you're starting to get a much better idea of what the root cause is. So now you can start applying these tools in reliability to apply to the actual problems that you're seeing in the field. Once the anomalies are detected, the respective waveforms help determine the root cause and allow utilities to categorize them. So once those waveforms are identified, categorized, they're saved in a repository and later used for AI application. So now let's take a look at how these intelligent grid sensors are installed. They can be installed with hot sticks or gloves. They're actually, there's a whole science behind how you deploy them. If you're using them for fault management, meaning to determine the type of fault and location, the sensors should be installed on feeders near sectionalizing equipment, right? Because every time you have a branch, the set of sensors on the main trunk line may not see the same types of signals or the magnitude of the signal that the laterals or the branch circuits would see. So there's a whole science behind it. As part of our consulting, we actually do that service for a lot of utilities. So if you have industrial customers running inductive three-phase motors, sensors can be used to improve power quality and ensure that phases and circuits are properly balanced. As part of my experience in a chemical company, I had to, one of my responsibilities was operating or maintaining the station that we had, which dropped from 138 kV to lower voltages for running our very high voltage motors and extruders and all that. So we used to get issues with our motors where our motors would only perform for half of their expected life. And so we did some studies when I was there as an engineer. Of course, you're going to try to determine that root cause. And what I determined during that period was that it was dirty power that was causing the majority of the issue with these motors. So you'll see that a lot with utilities. You'll see that large industrial organizations will blame the power company, and the power company will deflect. It's not always the power company's fault, but just to let you know, that is happening in the background. So these sensors are actually inductively powered from the line and are made to last for 10 to 20 years without any human intervention. So they basically operate, they're there to be line monitors sending data back to the platform. So once the sensors are hung and collecting and sending data back to the server, the platform runs fault location algorithms to help locate those faults. Today, many different location algorithms have been developed, with each method having its own merits, right? So I named three of them here. There's a simple impedance model that takes the impedance of the actual conductor and takes the magnitude of the fault and says, okay, based on a formula, this is where the fault is located. There's other more complex methodologies like the Takagi reactance model. And today, I think one of the most common forms is the traveling wave methodology.
This is an interesting point here, David. Going back to your taking care of the substation. Just the other day, I was talking to a municipality, and while they have fairly good reliability, their SAIDI numbers are in the low 60s. It's a relatively small municipality, but they also deliver water, fiber, and electricity to their township. And they're experiencing burning up, just dawned on me, they burned up two heavy lift hydraulic water pumps in the last year. And so they are saying to us, just the other day, they're saying, this is very interesting. We were talking about this technology, and they said, this might be able to help us understand what is causing these, pumps that are supposed to last 20 years are lasting less than 5. And then this traveling wave, some people really want to understand it. And it's a simple, the difference about that in impedance model, if you think of an impedance model, how much energy does it take to move a vehicle on a sandy beach? It takes a lot of energy, but if you use the same amount of energy to move that vehicle on a hard paved road, you're going to get a lot further. So that's where the impedance model comes in. And then the traveling wave is unique, and it's pretty cool, because think of dropping a pebble in a pond. Not only is the medium moving, but and you can see that visibly in the pond, but the elements of the water are moving with it, and which gives it a much, if you understand it, it's a much more accurate way to come up with a location, because the wave travels at a certain speed given the medium it's in, and it will take it only so far before it dissipates. So some of these techniques are really, really accurate. But the point I'm making here is they have to be applied correctly. But that's interesting. I realized, talking to that utility the other day, there might be a solution for them so they're not burning up water pumps.
Yeah. So part of what we do on a day-to-day basis is we take in this input, and we become consultants and experts in the industry to help with planning and deployment of the technology. So a new application can spring up at any time. So if we kind of get into a little bit more about the technology, the analytics platform, which allows for display of the waveforms and other essential data, is where the utility engineer can troubleshoot the line prior to dispatching a crew, right? So that's where the efficiency comes in. The platform allows for integration with other utility systems. So we can integrate this data with SCADA, DMS, ADMS, and OMS systems via DMP3 or any other protocol that those systems might utilize. And then it allows users to set up alerts based on event categories. So you can actually avoid false positive alerting or notifications by narrowing down what you send to the users and engineers. So users can add their own widgets ranging from waveforms, line charts, weather service data, instantaneous tables, and gauge charts, to name a few. But this is where the utility personnel can actually troubleshoot prior to going into the field. Another function of the software is to manage the fleet of sensors, right? So you have all these sensors out on your network, and you need to upgrade them. You need to tune them, and you don't want to have to take these sensors down to be able to do that. So sensor technology is becoming more and more sophisticated every day, so that if you're looking for a very different problem and trying to troubleshoot that problem on the same line that the other day you were troubleshooting a very common problem, you can actually tune those sensors to listen and indicate on that other problem. So that's important to understand. The technology that you select for detecting these faults is extremely important to understand. You don't want to have to interface with those sensors to be able to do some of these simple things. All right, so now let's look at a little bit more in detail on the, what we're talking about. How do you actually determine what these signatures are? What's causing them? So if we look at the anomalies themselves, what we call them is power line disturbances, or PLDs. They're defined as variations in alternating current, voltage, amplitude, frequency, and waveforms. So some of the terminology that you'll hear associated with PLDs are line sag or line swell, galloping, harmonics, intermittent voltage variations. There's a myriad of terms that utility operators and engineers use to define these PLDs. Basically, it's an anomaly that could cause harm to your system. So the solution platform measures the harmonics on a line. Harmonics can be caused from many sources. So one of the most common one is inverters, right? You have a PV field and you want to take that DC voltage and convert it to AC. those inverters cause quite a bit of harmonic frequencies onto your existing power lines. So these can be problematic for utilities because they need to understand what the effects are, right, on power quality. So these are typically defined by orders of magnitude on a fundamental frequency. So if I were to give you an example, what we're looking up in that diagram of that waveform, that's a sinusoidal waveform of the current, and that is a 60 hertz. So the sampling frequency is 60 hertz. Now, the little squiggles that you see on top of those are actually the PLDs. Those are orders of magnitude of that fundamental frequency. So it may be 3 times the fundamental frequency, or 180 hertz. It may be 100 times, maybe 600 hertz. So the point is, if we were to take those frequencies or transients, sometimes they'll be called, and overlay them on the fundamental waveform, you can actually see these in action. And this is what engineers will be doing to troubleshoot a line. So these transients may come in, and the one thing I can tell you for sure, after speaking to many utility personnel, is that they increase in frequency, and when they do increase in frequency, they usually lead to major outages. So there are many sources. Again, harmonics are one, trees, equipment failure, looming equipment failure, animals. So data scientists today are analyzing terabytes of data to try to find the patterns that recognize and differentiate these useful harmonics, right? They're useful because they're telling us something. They're actually data that we can turn into knowledge. So the idea is to, understand them and differentiate them from random noise. Random noise may be from interference, from radio signals, from other type of transients that can come across a power line. So understanding them, categorizing them, and using them in an AI system for comparison against future failures is key. Okay, so one way that we can determine, I said the increased power line disturbances that can lead to areas of concern, we use what's called a PLLD counter. So we actually take these line disturbances and we count them. If the frequency increases or increments, then we say, okay, there's something you need to look at. So in that case, we'll send a notification. The operator may send a notification to the line crew and say, hey, go out and check this area based on the locating capability. So if we look at the path to how to get to predictive modeling, everything is broken down to a simple process. This is that process for determining and categorizing the PLDs. So in the diagram, you can see that the system captures and reports these PLDs to utility operators. The utility engineers are informed that anomaly exists. At this point, the anomaly is just a hypothesis that needs to be validated, so they roll a line crew out there to troubleshoot. Once it is validated, the waveform is categorized as a signature, and now you have the workings of an AI system.
I might add here, as we look at these solutions, and the premise here is helping a utility be more reliable, lowering O&M. It's most important that utilities have, when they embark on these projects, these are journeys, these are destinations. And you need to understand that you have executive sponsorship, because as David's indicated several times, you're going to get this data will come in, okay? And this data has patterns, and we started with the patterns. And once you recognize the patterns, you're more confident in dispatching crews and sending them to look for certain characteristics. I noticed in some of the chats here, could the galloping lines potentially have been detected in Spain that may have caused the outage out there? Well, certainly. But without putting the system out there and without seeing what the galloping lines looked like, what their pattern was, having the sensors out there by themselves and this type of technology wouldn't have mattered, because It's the function that you collect the data, you analyze the data, you turn it into usable information. That pattern then is reused and reused and reused. And so it's really more complex than just looking at a waveform. It's multivariate data, right? There's the waveform, there's the wind that caused it. Was it high humidity? Was this during a growing season? I remember not too long ago, worked with the utility, and we had placed some sensors up, and not 2 weeks later, they called and said, your stuff works. I've never had a customer call and say your stuff works. They just assume it does. Well, they had seen a pattern emerging. It was grow season, March, and it had been very windy, and they saw these disturbance counters increasing. So they had sensors only outside the substation. And after day 2, after the second day of seeing the winds blowing and these PLDs occurring, they rode 7 miles outside the substation and found some tree branches had grown up between phase A and B, cut them down, the PLDs went to 0. So the stuff works, but you've got to go out and investigate and validate and demonstrate to leadership, and leadership's got to be behind it, because that rolling that crew costs money, and it's either sending the crew or using the technology to work smarter, not harder. So I'll kind of pause there, because my point here is if you're going to embark on this journey, it's most important to have executive sponsorship, because you're going to change work processes.
So thanks, Jim. Here's an example of a anomaly that was found. It was recorded, it was then located, and this is the process that was actually followed. So, the system detected it, reported on it. The disturbances were analyzed and categorized. The utility crew was dispatched. This is what Jim was talking about, validation. And then the vegetation was mitigated and the waveform was archived for later use. So exactly what Jim said, this is the typical process that occurs. So if we look at predictions for veg management, if the PLD meets certain amplitude and frequency measurements, the signatures is actually stored at that point, right? And then categorized and then cataloged, so that later we can, if we see a similar circumstance, then you can act on it. So disturbance counts are reported to operations. The software prescriptively notifies of these types of faults and informs operations of potential tree encroachment. So then the crew validates the waveforms, the crew goes to the location indicated by the sensor, and post-mitigation actions are recorded and archived. So I know we're running close to the hour. I want to leave some room for questions. So I'm going to leave it. This is our last slide, but basically, this repeats the process, and it's just a pattern that needs to be developed in your utility, and utilizing the tools, then you become much smarter, and lo and behold, before you know it, you have a full AI system for pattern recognition. So with that said, Jonathan, I think we'd like to open it up for any questions that the audience might have.
Absolutely. Thank you so much, Dave and Jim. So folks, we are now at the Q&A portion of the webinar. I know we only have a bit of time left. So we've already agreed with our presenters to continue the webinar 5 minutes after the hour, just to take some more time for questions. So our David and Jim, our first question that I want to highlight from our audience member, Ramesh, is it possible to bury the transmission line cables instead of overhead? Which is more economical in the long run? Feel free, either of you can feel free to jump in if you have the answer. Or
it's possible. It's very expensive. Okay, very, very expensive. And there's new transmission technologies with fiber cores that run hotter, run longer, don't have the sags. It's really transmission. When you think of the distance transmission lines have to go, not only that, the utility doesn't own where the transmission lines go. So you're going through state parks and people's backyards and across highways and over rivers and valleys and stuff. It's very, very costly to bury transmission lines. And it takes a long time. I know a utility that spent 15 years getting a permit to build a transmission line in the Pacific Northwest.
So I'll add a little bit to that. If anybody's heard of DLR or dynamic line rating, if you bury transmission lines, you would have no ability to run over capacity based on DLR principles, because the whole concept of dynamic line rating is that you have wind that will help cool that line down and allow you to carry a little more capacity or ampacity on that line.
Good point.
So,
Good point.
next question.
Thank you, Ramesh, for the question. Our next question for our audience member, David. David asks, in the recent power outage in Spain/Portugal, would sensors detect galloping transmission lines, which they believe was the cause?
Yes, I just addressed this one for David. Yes, the sensors do detect galloping lines. It's a matter of calibration and, understanding what that pattern looks like by, again, assessing. I've seen it in Southern California. I've worked with a utility out there years ago when you got the Santa Ana winds that come up off the ocean, and they'll have 70, 80 mile an hour gusts of wind in the valleys, and those lines will gallop, and they'll break free from their, insulators, suspension insulators. They'll gallop and they'll phase slap. And so having accelerometers and these types of abilities to understand when those lines are galloping and potentially phase slapping and dropping, molten to the ground, that's the first sign of a PSPS in California where everything needs to be shut down. So absolutely, they can do that.
All right. Thank you, David, for the question. This next question from our audience member, can't see the name, but I believe it is our audience member, Roger. Roger asks, residential smart meters have recently been deployed in my area. I assume these provide power quality and interruption data to AI systems as well, also?
Yes. So AMI data replaced a customer calling in a power outage, right? So now with AMI, utilities are much smarter. When an entire neighborhood goes out because of a power failure, then obviously they get that through the AMI system. However, the AMI system cannot detect what type of fault it was or where the fault is located. So, most utilities will actually triangulate AMI data with sensor data to become a little bit more knowledgeable on that particular outage. So good question.
This next question, audience member Thomas asked, what does this offer that an advanced line relay like a SEL 411L doesn't? Any thoughts?
I'm not familiar with an SEL 411. I'm imagining that's a Schweitzer Electric Lab device, but what we can offer over a typical relay is location and identification. So relays may be able to detect small amplitude faults, small amplitude current faults. However, they can't locate those faults. So you need a little bit more power. You need an analytics system to help you determine those types of things. So sorry, I didn't fully answer the question because I'm not familiar with that equipment, but
yeah, I hope that answers your question, Thomas. If not, feel free to elaborate on what an SEL is, and we'd be happy to go back and address it. Our next question, alien vibration can cause fatigue, so stock bridge dampers are used to mitigate the movement. These could be potential sensors. So what is the limitation of dampers?
This is outside of my expertise. So I definitely don't want to try to answer something that I can't answer knowledgeably. So
no problem.
Jim,
Appreciate the question. No problem. Appreciate the question. This next question from our audience member, Fabio, asked, can these feeder-mounted sensors detect early mechanical instabilities, such as the onset of conductor galloping, before they impact power quality?
I'll take that one, David. The answer is yes. We didn't get a chance, but I'll speak to another utility. David and I were going through our biweekly data review of the utility not so long ago, and we started to see a whole bunch of anomalies. And so when we pointed these out, we asked the utility, there was a pattern there. And we asked the utility, and they came back and said, yes, we had customers complaining about, brownouts, flickering lights, and these types of things. And when we patrolled it, we found that a cutout was failing. And so by virtue of that, we were able to help the utility capture what that pattern was, because it happened over a period of days, not just once. So there was an emerging pattern there, and the calls were coming in. And so again, whether the conductor's galloping, whether perhaps that dampener has failed, that suspension insulator has failed, and now you have a floating conductor, or even so much as a splice is beginning to fail. Because what are the majors in the distribution? We see cutouts, splices, and insulators. Common points of failure, which are all potential sources for ignition for vegetation management, but all can be identified early on and patrolled and validated, so you can at least be proactive, and in some cases start to get predictive that this pattern is emerging and this is going to fail. It's kind of like saying, we know there'll be a murder in Chicago this weekend, but where and when? So, by more recognition of patterns, more understanding of what it looks like, and by turning, somebody said, we need information and knowledge, not more data. But it's the data that you use to drive your information, and it's the information that provides you knowledge.
Thank you for that, Jim. And I hope that answers your question. We'll address two more questions. This next question from our audience member, Dave. Dave asked, what's being done to protect the North American grid from CMEs and hemp? We did get a question from our audience member asking if you might be able to define what CMEs and hemp are as well. If you have any input on that.
I'm not familiar with either term, so again, I'd prefer not to try to butcher the answer.
No problem. Dave, if you might be able to elaborate on what those are, feel free to do so. And for those folks whose questions we cannot get to today, feel free to reach out directly to Jim and David. We provided their contact information on the screen in front of us on stream. So yes, I do apologize in advance if we're not able to get to your question. So this last question, our audience member, Din, this is an interesting topic. I would love to see the details on how you built the AI machine learning system.
Jim, you want to take that one, or you want me to?
Love to share it with you, but it's our secret sauce. It's our IP. Yeah, I mean, this is something we couldn't share the details of how we built it or what is in it.
I guess as at a high level, we can let Din know that the idea of the whole presentation was actually pattern recognition and machine learning and understanding those patterns. So once you have sufficient data that has been validated through hypothesis validation, then you can start building that AI model. But yeah, as far as what's in the secret sauce, we can't necessarily share that.
Understandable, no problem. Appreciate your interest in. All right, folks. Unfortunately, we are out of time. I know we could probably go on and on about this, but Jim and David, thank you both so much for joining us today and providing your expert insights on how AI and sensor technologies are reshaping grid performance and how EGM is leading the forefront in this initiative as well. Really great. Appreciate having you both with us today.
Thank you.
We'll take the comments, and if they make sense, we'll make a public posting back to IEEE, and that way some of these questions can be answered, so because we couldn't address them live.
Absolutely, and we'll forward all those questions that we received to to our presenters. Again, to our audience members, we have provided the contact information on screen, so feel free to reach out directly. And also, thank you to our audience for tuning in for your great questions as well.
Great.
A few quick announcements before we end things off today. First, IEEE-USA is now receiving nominations for the 2025 IEEE-USA Awards. Every year, the IEEE-USA Awards are given to recognize professionalism, technical achievement, and literary contributions to public awareness and understanding of the engineering professions in the United States. You can find details on each award, eligibility, and the nomination process on our website. The link has been provided in the comment section. Next up, we're just a little over 2 weeks until our IEEE-USA Innovation, Workforce, and Research Conference, or iWork, event on May 15th in Portland, Maine. This full-day summit will provide a platform for meeting potential partners in industry, academia, and government, exploring federal technology initiatives and learning about government's small business programs that foster innovation in the Northeast, and is an event you don't want to miss. Finally, cabins are filling up quickly for IEEE-USA's cruise to the Western Caribbean this fall, with most of the suite level cabins almost sold out. For those who have joined us on our previous 2 cruises, you already know the incredible experiences and connections this event offers. For first timers, this is your chance to create unforgettable memories, enjoy great company, and embark on a journey packed with excitement. Don't miss out. Secure your cabin today and join us for an adventure you won't forget. If you enjoyed the content presented in today's webinar, be sure to check out our extensive catalog of other presentations and publications available on demand on our website for your viewing pleasure. If you haven't yet, please be sure to like and subscribe to our social media channels. And don't forget to check back daily for updates on upcoming events. Have a great day, everyone.
Hi, I'm Dr. Ashanti Maxwell. I'm an associate professor in electrical engineering at the University of Southern Maine. I'm very excited to welcome all of you for the IEEE-USA Innovation, Workforce, Research and Development Conference, which will be held on May 15th at the University of Southern Maine Portland campus. If you are a STEM entrepreneur or if you are somebody who wants to start your business in Maine, this will be your conference. Our goal is to bring resources and representatives from the industry, academia, as well as from the government into one place. So if you are a change maker in Maine or would like to be one, this is your opportunity. And I'll see you on May 15th.